All right, well, thank you for the introduction. So I'm going to give a bit of a different view of AI than you typically might see at an AI hardware presentation. So I'm going to look at things like what would happen to the markets if a $10,000 GPU only cost $5 and was the size of a shirt button. Or the fact that the only way to get a frictionless experience for developers is to massively increase the amount of compute available. Or the fact that the end of Moore's law means trouble for the way the industry currently designs chips. But before that, let's first briefly paint that future vision of AI that I'm sure you all have likely heard before. So robots becoming smarter and more adaptable. They'll eventually take care of mundane and everyday tasks like cleaning and delivery, saving us many hours per week. So AI is enabling autonomous vehicles. The average American spends 10 hours a week behind the wheel. So imagine what you could do if you had that time back for more fun things. And AI is already delivering major advancements in healthcare through smarter medical devices, more accurate predictions, and automated assistance during surgery. And better education by giving children a more personalized and interactive experience. So again, AI has a huge amount of promise. So why have we not seen that massive explosion in AI adoption around the world like we have with other technologies like smartphones? And I see it as a problem of scale. So these are compute-intensive algorithms that currently need massive, expensive hardware. And to get the layers of abstraction needed for easy development, we'll need another order of magnitude of compute power on top of that. And this compute will need to go anywhere. Now, we've seen this many times before, with mainframe computers that eventually broke through to personal computers, and giant cell phone bricks that eventually became the most successful compute platform of all time. And what are the keys? Low cost, lots of compute, and layers of abstraction on top of that for developers to leverage that compute. And a lot of these applications need to happen at the edge due to latency, throughput, and network availability constraints. So here, cost and power are critical because you cannot amortize that hardware over many users like you can in the data center. So this is the challenge that Mythic solves for AI. How do we deploy AI for hundreds of applications running on potentially hundreds of different devices for billions of users around the world? There are major limitations of today's hardware. The battery life, the cost, the heat, the size, difficult design environments. But what we're going to demonstrate that is if we can drive the cost and the power of AI hardware down, we're going to open up massive new market opportunities for AI. So cost going down, market size exponentially increasing. This is what defines the semiconductor market. It's not about $10,000 pieces of hardware. It's about creating massive new markets through worldwide scaling. So this example here shows the market for flash memory from 1999 to 2011. So you see here that the cost per gigabyte has fallen exponentially over those years. Now, you would think for suppliers and makers of flash memory, the cost falling exponentially would be very bad for them. But the reality is the market actually responds in a massive explosion of revenue and opportunity. This is because it leads to widespread adoption across many devices and a huge market increase. Same story with Wi-Fi chipsets. Shrinking of components, taking what was once on large boards and putting it into a single chip, driving down the costs. This opened up massive new markets and billions of revenue for Wi-Fi chips. So falling costs, increasing market. Same with CMOS image sensors. As the cost per megapixel fell over 10 years, you saw massive adoption and market size increase across a huge range of products. So smartphones adopted them, and security cameras proliferated due to the lower costs. So this is what we're going to show. The first thing we'll show is that AI and DNN hardware is going to follow the same trends. We'll analyze the market demand of AI hardware as it relates to price and show that there are massive potential markets waiting to be unlocked. But a lot of those previous plummets in price that I showed were due to Moore's law scaling. So we're going to show how Moore's law is coming to an end. And this means that new creative approaches, like what we're doing at Mythic, are going to need to be executed in order to drive this market expansion. We can no longer just rely on Moore's law, like we can with all those markets I showed. So first thing to point out with this presentation, and with Mythic as a company, is that we focus on inference. So in other words, the deployment of compute-intensive AI algorithms out into the world after they've been trained. So training hardware is going to be a vital component in the inference ecosystem, but the economics and the scaling of it are completely different than what we're talking about here for inference. Inference is all about massive scale-up, both inside and outside the data center, often in areas where cost and power are critical. Because again, you cannot amortize the hardware across multiple users, and you don't have a kilowatt of power to supply to the hardware. So to reiterate before, we envision a future world where there is powerful AI hardware in every device, solving major societal challenges, enabling new applications we haven't even thought of before. But to get there, we have to overcome this chicken and egg problem. So platforms like cell phones and IoT would need the AI hardware in place so developers can build this future. The hardware needs to be far more powerful than what we have now to enable easy development, but device makers are cost conscious. They need to justify that new AI hardware in their device will actually yield dividends. But we see a solution to that problem. We believe that AI can improve the existing functionality in all of these platforms. We think there's massive markets already in the making based on what device makers want right now for their hardware. But first, in order to make that happen, the cost of compute needs to fall dramatically. So to start, let's first take a look at what markets are driving the hardware and semiconductor industry, and specifically focus on the ones that AI will affect. So on the left is revenue, and on the right is units shipped per year. So by far, the biggest driver of the semiconductor industry is consumer electronics. That's things like laptops, smartphones, TVs. And automotive is large and rapidly growing market, as is IoT. And you'll see here at the bottom that AI server inference is nascent right now, but we also see that market growing rapidly. Nevertheless, getting into these existing platforms that are already massive is a guaranteed success. So here's the model we use as we work through these different markets and analyze them. This is the model we use for pricing the compute that we need to put into these devices. So one thing to notice, as you concentrate compute and put more and more compute on a single chip, the price increases exponentially. And again, also, these metrics I'm about to go through, this is an approximation from a variety of sources. So we're trying to build a framework here. We're not trying to build a highly accurate investment thesis, so you'll have to bear with me on that. But let's assume that 1 unit of compute is equal to 1 present-day consumer desktop GPU right now in 2018, and let's say it costs $500. So that's 1 unit of compute. And let's assume that we can get 1/10 of that desktop GPU from some sort of IP core that you can put into a mobile GPU, and that would be a $1 incremental price in the chip. Now let's assume those monster aircraft carrier-sized chips that we're seeing coming out to take on NVIDIA have the equivalent compute of 10 desktop GPUs, and they cost $20,000. So right now, every cell phone already has the 0.1 GPU compute equivalent inside of it, since every cell phone has a mobile GPU and a CPU. So we're going to start running through some thought experiments. Like, what if you can offer a chip suitable for a cell phone for $10 that has the equivalent compute of 10 desktop GPUs? How would the cell phone market respond? So first thing, with that pricing framework, let's start with consumer electronics, like smartphones, tablets, and laptops. And let's look at how purchasing decisions are made by the users and device makers. So we'll see on smartphones that people spend a lot of time playing games, taking pictures, using social media. You can also look at the bill of materials of the smartphone and see how much device makers are willing to spend for these features. So knowing that we're working with this platform, we can ask the question, what can AI impact that matters right now for consumer electronics? So first, just to run through some examples of how we can impact our present consumer electronics, not massive new markets, but our current devices. We can look at speech quality. So this is a demo from Babel Labs of neural network speech enhancement.
Buses.
This is the original.
And right about now, we're going to get a lot of noise as the traffic is moving. So hopefully, our speech enhancement.
And this is enhanced with neural networks.
Trucks, buses. And right about now, we're going to get a lot of noise as the traffic is moving. So hopefully, our speech enhancement algorithm.
Neural networks can also make the small cell phone cameras look like a professional-grade camera. It can also do impossible tasks like the one we're showing here. So this is a neural network algorithm that we've developed that takes a picture or video from a nearly completely dark environment and makes it look like daylight. So enhancing the camera. What about next-generation gaming on our consumer electronics powered by AI? So this is a demonstration by NVIDIA for speeding up ray tracing using neural networks. So with a neural network denoiser, you can actually bounce far fewer rays around the scene, and you can still get photorealistic results. So all the way on the right is their bare minimum number of rays bouncing around for ray tracing. The image in the middle, they're cleaning that up using neural networks. And this is one of the key steps to getting real-time ray tracing on consumer hardware. And it's even been demonstrated that you can use neural networks to potentially speed up Markov chain Monte Carlo. So now this is actually the key algorithm in ray tracing that models how the light bounces around. So now we're accelerating almost all the parts of ray tracing using neural networks. And this DNN algorithm also has implications for other spaces like protein folding and Bayesian inference. And AI is going to drive breakthrough new user experiences for consumer electronics by powering the perception stacks of AR and VR. And AI can deliver higher quality video at lower bit rates through post-compression noise cleanup of existing compression algorithms. And it can also deliver more powerful compression algorithms that use deep neural networks to do the encoding and estimation. So with all those examples I gave, hopefully this establishes that AI can impact what matters right now for consumer electronics. So now we're going to look at pricing and how that plays into all that. So we have an idea of the kinds of algorithm stacks we want to run. We have an idea of the compute power needed to run those very advanced neural networks. We know what desires drive consumer electronics. So now we can build a framework of adoption based on cost. And this framework takes into account the fact that we want to be running far more algorithms with greater complexity and layers of abstraction compared to what we can do now. So here's how this framework works. As an example, we make the assumption for high-end mobile phones that if you can deliver one desktop GPU equivalent chip in a low-power form factor for $10, we assume that 25% of smartphones would eventually adopt that chip. And if you can deliver the equivalent of 10 desktop GPUs in a single low-power chip for $10, that 75% of smartphones would eventually adopt that chip. And I think based on every example we showed previously, that's a fairly safe assumption. And then we can run that same exercise for other consumer electronic devices like PCs, laptops, and tablets using their bill of materials, and we can start to get a sense of how big this market might be for AI chips that are far more powerful. And remember, these aren't meant to be highly accurate future projections. These are instead thought experiments for how these products will evolve as this price of AI compute drops. And remember, the history in the semi industry tells us this. It tells us as the price of compute falls, massive new markets and revenue opportunities open up. And now let's do the same for automotive. So we can look at the rate at which automotive safety features get adopted. This is actually from 1971, so it goes pretty far back. And we can look at what percentage of cost of the car goes to electronics and how much is spent on each system in the car. And we know that the key to next-level driver safety systems is powerful algorithms. These are running on cameras and new sensors that are far more perceptive than what we have in cars right now. And we also know that these sensor streams can produce a huge amount of data. And processing at higher resolutions leads to much better results. So compare a 700 by 700 image to a 300 by 300 image when detecting cars and stop signs. So even outside of autonomous functionality, just focusing on driver safety systems, every vehicle on the road can benefit from massive compute and powerful AI. So taking all that and putting it together, now we can come up with an idea of rate of adoption of these neural network chips for safety systems in cars as the cost drops. So high-end safety systems that were exotic in the 80s and 90s are becoming standard now. So rather than looking at the autonomous market with those big $15,000 boxes, we're actually looking at all 88 million cars shipped every year and seeing how the rate of DNN-powered systems will increase with the falling cost of compute. And by the way, this is not considering autonomous driving again. This is not moonshot technology. We're focusing on existing platforms. Things like autonomous vehicles, delivery drones, flying cars. That's all going to be market volume that's basically a cherry on top of everything we're talking about here. And we can keep going for all these other markets. And we say we can apply the same logic of falling cost of compute to the high-end side of IoT. So our definition of IoT here is things like robotics and smart city, agriculture, safety, security, surveillance. These are all applications that benefit from processing big streams of data, like video. And then the server market for inference is a little tougher to predict, since the divide between edge, on-premise, and server, edge, on-premise server, and hyperscale gets pretty hazy. Plus, something to point out here is that you're seeing companies like Google and Facebook actually push all of their machine learning workloads into the DNN domain, things like search and recommendation. So this trend may expand broadly to a lot of different companies and domains, or it may remain localized to these very large, highly capable companies like Google and Facebook. It's just too hard to predict. But what we can at least do is make assumptions about the cost and power budget of the servers and see how many AI chips can you pack into a single machine. So now we're going to do a quick preview of the third part of this presentation. So these graphs show an estimation of the cost of an inference chip with an equivalent to 0.1, 1, and 10 GPUs. And I mean a current consumer-grade GPU in 2018. So it's equivalent compute. And we estimate how the cost will fall over the next 5 years based on past improvements we've seen in highly parallel compute hardware. So what we'll show is that with Moore's law over, this is going to mean very slow improvements for all digital inference architectures. So here we show digital architectures with Moore's law scaling and projecting for the fact that it's really tapering off and coming to an end. We show that here in black. So how can we shift these cost curves down? Because remember, pushing these cost curves down means faster-paced improvements in cost, and it also means opening up massive new market potential. So later, we'll show how Mythic's new analog approaches outpaces Moore's law. So the improvements to our product through the unique scaling of our compute and memory shown here in red. So now we can put all of this together, form a big picture of the market potential as these costs plummet. So this is just with plain old Moore's law scaling. It was that black curve I was showing previously. And what we're doing is we're essentially taking the price of compute over the years, we're taking the market size in terms of units sold, and we're taking the adoption curves that I was showing as I flipped through all those different markets. And you'll see here, with just plain old Moore's law scaling, you're looking at the markets growing to about $18 billion. And this is really driven by the server inference, it's driven by high-end computers, and it's driven by limited deployments in high-end cars. This is because the hardware will continue to be expensive. So amortizing all those costs over many users, like in server and autonomous fleets, that's going to be the only way that we can really widely deploy these solutions to the world. So now let's look at those mythic scaling curves that I showed previously and apply them to the same framework here. So again, price of compute, units sold, adoption rate, now times the falling in price that mythic can deliver with our more than more scaling. So we can drive the cost down far beyond what Moore's law is going to allow us to do. Now we estimate that an additional $40 billion in market value is going to be created by that. And this is going to be driven by large adoption in consumer electronics, automobiles, and IoT. So putting all these graphs together, so this represents the total addressable market, or TAM, with mythic in red and digital Moore's law scaling in gray. So by rapidly pushing down the cost and the power of AI compute, you can see that we can create tens of billions of dollars in additional market opportunity. And we'll also show that continued growth beyond the market, or continued growth beyond 2021, we show that by just using comparables of other explosive chip technologies from the past. Now, in reality, the adoption is not going to be instantaneous. So the adoption and the actual market value generated each year is not going to follow these curves, because adoption is going to be a subset of these curves. Adoption always lags behind potential. But more importantly, these lower costs get powerful AI into every device. So not only does it add tremendous value to the existing features of these products, but it opens up the door to all the amazing future visionary applications of AI that we talked about earlier, and likely some new applications that no one has even thought of before. Okay, so now how will mythic drive that massive demand? This is answering the how of that big drop in price, the big drops in those price curves that I showed previously. So to get a hint of what drives massive demand, let's look at just computing in general over the last 40 years and see what's driven massive growth in past compute platforms. And let's look at how it relates to AI. So we'll talk about ease of developing and deploying these things to users and reducing the friction for developers. We'll talk about power consumption, and we'll talk about cost. So first, let's look at usability and ease of development. So right now, what we're seeing in the AI industry is a trend towards highly compact implementations of neural networks tied to low-level CPU optimization. Now, this was much like GUI programming in the 1980s, where everything was rigid and very tightly tied to the CPU. Now, the computing world does not stay at that paradigm for long. More compute leads to easier development, and it's going to lead to easier AI development because it allows us to build powerful frameworks and layers of abstraction on top of existing frameworks, just like you saw with GUIs then and now. So more compute means easier development. So at Mythic, we're helping this ecosystem in 3 ways. So first, we're giving a powerful set of tools that plug into the popular training ecosystems. Things like compilers, estimators, drivers. Second, we're eliminating DRAM from our systems. DRAM is the cause of much headache with these existing platforms. DRAM is expensive, and it has to be shared with other parts of the system. So this leads to a lot of lag and uncertainty when you're running these algorithms. It makes it really hard to design a responsive, low-latency system. And finally, we're going to be giving reference neural networks that take advantage of the significant increase in compute that we're delivering for inference. These are going to be far more powerful and robust than compact neural networks like Google MobileNet. And you can see in that on the right there the difference between lightweight neural networks like Google MobileNet and more powerful neural networks like ResNet. The lightweight stuff misses things. The next thing that is important is lower power and longer battery life. This has actually been equally as important to the explosion of the semiconductor industry as cost. They're actually equally as important. Now, the actual arithmetic does not burn a lot of power. The more difficult, no more clicker. The more difficult task is getting the data out of memory and to the arithmetic units at the right time. So low power AI compute is all about memory. Finally, how do we get more compute per dollar? So we eliminate external memory. Again, noticing a pattern here, DRAM is the cause of a huge amount of frustration. We eliminate external memory and keep everything on chip. External memory leads to performance-killing bottlenecks when you're running really intensive applications like AI. So we keep the memory and compute as close as possible together. Sending data across the chip also kills performance. And we make the compute and memory as dense as possible to fit as much as we can, to maximize what we're putting on the chip. So, can digital architectures that rely on Moore's law scaling for improvements drive down cost and power? So we should point out here that Moore's law scaling has recently hit some roadblocks. You have to wait a few years for the process to be qualified. Now you have to spend hundreds of millions of dollars in development for bleeding-edge technologies. The mask sets cost tens of millions of dollars. And what do you get out of that? You get a 2x gain. For all that wait, for the 3 years of wait, for the hundreds of millions of dollars, you get a 2x gain. So this is the state of Moore's law right now. And if people need proof that keeping up with Moore's law is becoming more and more difficult, just look at the recent news about the state of the art of advanced semiconductor process nodes. So, in a post-Moore's law world, how do we drive this continuous drop in cost and power that's going to open up that $40 billion in market opportunity that I showed previously? And remember, this is not about just moving away from von Neumann and x86 and graphics GPUs. The challenge goes much deeper, and it's much simpler. It's simply that we cannot rely on SRAM and cache. That's all digital memory, and digital memory relies on Moore's law scaling. Oh, went too far, sorry. And the same goes for digital logic. We also can't rely on shrinking the models or optimizing for the CPU, because history tells us that applications and algorithms get bigger. Layers of abstraction pile up. So what do we do if we can't rely on Moore's law, and Moore's law is tightly coupled to all the things that matter for digital architectures? So AI inference is a very unique workload. It has relaxed constraints. So this lets us go beyond digital. So here's what we do differently at Mythic. So we store a single 8-bit value. Sorry, we store an 8-bit value on a single flash transistor. Oh, thanks. That is 50 times more dense than the SRAM that everyone else uses. And analog processing makes it so we never actually have to pull those values out of memory. And it's how we get the performance of a desktop GPU in a single chip at 100 times lower power. And we wrap all that up in a digital interface to the analog blocks so we can get reliable 8-bit computation across any operating condition. And this lets us build a flexible digital architecture that can run TensorFlow graphs in a tiny chip. So we're pushing a new technology with significant memory density advantages and 100 times lower power compared to alternative approaches. And this is all, by the way, in a 40-nanometer process. This is a low-cost process. It has lots of foundry capacity for quick ramp-up. 20 times lower mass cost than 14 or 10 nanometer. And we have lots of room for continued improvement since we reset the clock on Moore's Law. And we didn't compromise on the software ecosystem either. So by blending digital and analog together, we can still have a flexible, programmable neural network processor that can run any style of neural network. So our prototype chip that we've been testing and our compiler that's still under development allows us to benchmark against mobile solutions from all the big companies. So on the left is energy burn, so energy per multiply accumulate, where lower is better. And on the right is performance, where higher is better. And this is running ResNet 50, so it's running a large, beefy neural network. And it's also worth pointing out that the second place competitor on this chart is the NVIDIA Jetson. That's a massive $400 product. That's a massive chip, and it's a $400 product. So not really the cost-efficient thing that we've been talking about. But the future also looks bright for us with continued 10x improvements. So every other AI chip company is going to be stuck at the end of Moore's Law with their all-digital designs. So we're the only company that actually has many avenues of improvement beyond Moore's Law. From noise-tolerant neural network design that lets us relax the hardware and analog constraints significantly, to new circuits that continue to push down the innovative path that we've been trailblazing, to new device materials and 3D stacking of the non-volatile memory that greatly increases the density of neurons and synapses in our chips. So I hope this was informative. My objective here was to move the discussion of AI hardware away from abstract claims about TOPS per watt and post-GPU computer architectures. I instead wanted to put out a call to action that the objective of the AI hardware community, especially around inference, should be to continually push the cost of the hardware down, make it low power, and make it frictionless to develop for. This has been the formula of success for the semiconductor industry for the last 40 years. It opens up massive new markets. And it's going to drive the future AI-powered world that we've all been looking forward to. So thank you very much for listening. Happy to answer any questions. Thank you.
So we have time for a few questions, and I'll pass on the mic.
Just a quick question about your analog architecture. How do you actually load a model onto your tiles?
Yep. So the analog is actually just it's a matrix multiply engine. So if you can separate out all the matrix multiplies from the neural network, those map onto the analog, and then all the other things like nonlinearities and other functions get mapped onto the digital parts of the architecture. So the compiler actually does all the work. So you're really just programming the matrices into the analog blocks, and then the compiler takes care of all the other code generation to coordinate everything.
Does the loading process take a long time?
No, it's just like programming flash memory, and it's parallel, so no, it can be very quick. It's not on the order of second. It's not like, on the order of milliseconds or even like a second. It might be on the order of 10 seconds or 15 seconds. Yeah, we're working on speeding up the programming routine right now, but it's not like minutes or hours either. Yeah. Cool.
Okay. If nobody has a question, one quick one.
One question right there.
Okay, great.
Oh.
So are you strictly targeting this as, you're talking about consumer market and user application. Are you targeting entry, though, into some of the server, corporate, enterprise, whether it be cloud, on-prem, kind of a GP replacement market as a starting point to fund kind of eventually that growth into consumer? Or kind of what's that strategy?
That's the proper strategy in this case because, as a startup, you still have to target those high-value markets initially as you're ramping up. And so we're putting a lot of focus on video, especially on-prem video processing. Maybe you have hundreds of cameras coming into a box, things like that. That's our initial focus. And then, as you build up traction, you can start going after those consumer markets once you're a little more stable and mature. Yeah. Yeah, right there.
So any comparison with the Intel Movidius chip?
Yeah, so Movidius.
Could you repeat the question, please?
So any comparison to the Intel Movidius chip. So Intel Movidius chip is a more conventional digital architecture. It's processor-based. It has an external DRAM memory chip that causes a lot of bottlenecks So as you add more neural networks into the system, you're squeezing more things through that bottleneck and you get a big slowdown. We've eliminated those DRAM interfaces, so as you add more neural networks onto our chip, you actually don't have any drop in power, or sorry, drop in performance. Yep.
Just another question.
Yeah.
How big of an array of tiles have you tested working with? How does that scale?
It scales very easily. You just tile more, put more tiles down. Because you don't have any external DRAM interface, you no longer have that bottleneck. You know, as you scale up the tiles, with DRAM, you'd have to still squeeze more and more stuff through the DRAM. But for us, we don't have any external memory to rely on. So as we add more tiles, we're effectively adding more compute linearly. No, because typically the communication among tiles is very local. So no, we haven't seen any timing issues. And we've even, we even have the potential to do a reticle-sized chip, which would be this, monster low-power AI inference chip if we wanted to. Like, that's how well it scales.
So quick last question here.
Yeah, last question right over there.
How are you approaching the task of making the transition for people who develop in popular frameworks to go from inferencing on existing hardware to Mythic? How is the Mythic software stack plugging into the existing frameworks?
So there's a few keys there. The first is, use things like TensorFlow as the entry point for your compiler, so they don't really have to do anything differently. Automate the quantization, the quantization sparsity, all the compression, all that. So make a completely push button from TensorFlow to having a binary that runs on the chip is the first step. The second step is have application drivers that make it really easy to pipe video into the chip, things like that, and have a really robust API for the host system that it plugs into. Yeah. All right, so I think that's all the time we have. Yeah, thank you.